record at the very beginning of the Q&A review session today. And the first question or topic that we talked about was, when should or should you not use double bonds in a Lewis structure? And so I went through an example with SO4 2 minus, so 6 plus 2 for the negative charge gives us a total of 32 valence electrons, so essential sulfur, 4 oxygens. The O's. All the way around the O's, a 2 plus formal charge on sulfur, and so for formal charge, forgot to hit record at the beginning of our review session today, and the first question that we had talked about that I'll go over here today in this separate video is about when and when not to use multiple bonds in Lewis structures and dealing with those within molecules like an SO4 2 minus and dealing with their Lewis structure. So let's count up our valence electrons so we can see what's going on. 6 for sulfur, 4 times 6 for O, plus 2 for a negative charge. Remember, if you're adding electrons for negative charge structures, taking them away for cations. So we have 32 total valence electrons. So we have a Lewis structure. Starts with 4 single bonded oxygens to sulfur. Then count our electrons used versus available. So that's all 32 electrons, so none left over to put on sulfur. And so this is a valid Lewis structure for sulfate because sulfur satisfying the octet role has 8 electrons surrounding it. If we want to calculate formal charges, we can do so. The formal charge of oxygen should have 6 electrons for neutral charge. We have 7 electrons around each O. That's a -1 formal charge for each of these oxygens. And then the formal charge of sulfur should have 6, that's its valence count, only has 4 after we cut the bonds in half. Now your formal charge, you can take the valence count, the valence electrons for an atom, minus all the non-bonding electrons and minus 1/2 of the bonding electrons. So you can add up all the bonding electron pairs, all the non-bonding electron pairs. We're taking half of the bonding pairs. So if you just want to double check this for sulfur, you'd have 6 is your valence count, and then minus 0 non-bonding electrons, and then minus 1/2 times 8 bonding electrons. So 6 minus 4 is plus 2. And so plus 2 is our formal charge on sulfur. All the formal charges should add up to the overall charge. So minus 1 times 4 plus 2 is minus 2 overall, which is what we expect for the sulfate ion. So now the question for sulfate is, should we alternatively go to a Lewis structure that looks like this? And you might think this is a good Lewis structure, and the reason why would be we've minimized the magnitudes of formal charge, which is generally good. So we've gone from what was minus O's now to 0 O's. We've made this structure by making double bonds. Here, we've reduced these formal charges down to 0. Sulfur is now 6 minus 6 for 0 as well. So should we minimize magnitudes of formal charge or just leave them as single bonds? Well, when we get into molecules that are tetrahedral, like sulfur is here, 4 total domains, tetrahedral, we see that if we expect a double bond to be a sigma and a pi, we have a hard time understanding where we get a pi bond when I don't have leftover hybrid orbitals on a sulfur atom that's sp3 hybridized. We think of sp or sp2 of having leftover p orbitals that can hybridize or can overlap with other p orbitals to make pi bonds. I don't get that with sulfur here. In fact, we have a tetrahedral molecule. So we have a sulfur that's tetrahedral. And so I think it's probably best. And our book leaves a little bit ambiguous in terms of which one of these 2 Lewis structures is best. But I think the one that's best is the one with negatives across all the O's and a plus 2 on the sulfur. And that lets you clearly see that all of your oxygens are equivalent in bond distance because they're the same type. They're all single bonds. And if you do want to go with a double bonded structure, you have to somehow picture that you have all of these resonance structures. We have 2 double bonds, 2 singles. You have all the permutations. So double bond, double bond. I'm not going to go through them all, but the idea is somehow you resonate those 2 double bonds through the structure and you end up with 4 equivalent bonds nevertheless. So the key to me is Whether or not you want to think sulfate has 4 single bonds or 2 single and 2 double that resonate through the molecule, the key is the 4 bonds in sulfate have the same bond length. I don't think we're going to ask you a question on what's the best quote unquote Lewis structure for sulfate. If we did, I think it's this, but we're not going to ask you that question. The question we're going to ask is, can you describe the bonding in sulfate for equivalent SO bonds of equal length to each other? You're not going to have 2 shorter bonds or 2 longer bonds. You don't have an A to B to C situation going on. It's never A, it's never B. It's always the composite or the average. So it's one of these 2 structures here that are really the best, either through the concept of resonance or just through showing 4 single bonds. Deviated a little, but just as a reminder after this structure to look at something like NCl4 plus, where we have to take charge away. So 5 plus 7 times 4 minus 1 for that charge. And so that gives us a total of 32 electrons as well. So a very similar Lewis structure with the central nitrogen for chlorines. On the chlorine atoms, that's all 32 electrons. 32 minus 32. Because we have nitrogen, it has its octet filled, but has a positive formal charge. Chlorines are all 0 minus 0, or 7 minus 7 for 0 formal charges. And so plus charge residing on the nitrogen. And so then that was our Lewis structure here. Just a reminder that we take electrons away from cation Lewis structures, we add them onto anion Lewis structures, like we did adding 2 electrons for the sulfate ion. Afterwards, I kind of hit play on the video, and you can pick up from where the video begins. There's a link. The video was presented in Zoom, so I just used the Zoom video that's provided like by an email link. So I just posted the video. It's not going to be uploaded to YouTube like most of my videos.